Alright, so welcome to orbit determination. The first lecture that we're going to cover is orbit determination concepts. If you were watching the lectures before, welcome back. If you haven't been and this is your first time, welcome. So our class schedule is going to be Monday, Wednesday, Friday. Obviously I was dealing with some family issues, and so this is actually our first lecture starting the spring semester. The syllabus is available at the link. You'll be provided these slides later so that you can go ahead and go look it up. If you have already signed up for the email updates, it's on that same page if you just scroll down. And when you're working through the material, if you have a question, I'd prefer that you leave it on the YouTube page. I want you guys to work together and have discussions and help each other work through the material. It's only better, you learn it if you're teaching others, right? So be collaborative and help each other. And that would be the best place to answer questions or to post questions. So what we're going to do today is we're going to run through what is an orbit determination problem or an OD problem. Then we're going to step into the dynamic system, because obviously that's what an orbit is, or a satellite as it's moving around. What goes into estimation, observations, and why is linearization and the state transition matrix important. And then I'm going to leave you with an example problem that I want you to have solved by Monday. And yeah, let's go ahead and get started. So orbit determination is essentially guessing where a satellite is. So the quote that I really enjoy from the textbook, is: the problem of determining the best estimate of the state of a spacecraft whose initial state is unknown from observations influenced by random and systematic errors using a mathematical model that is not exact is the problem of state estimation, or orbit determination. So essentially, don't know where it is, or don't know where it started. We're not sure if our observations are correct, and we're using a mathematical model that we know is not exact. But you know what? We're going to guess where it is, and we're going to use those three faulty things in order to provide the best estimate. So in this course, we're going to focus especially on satellites. We're not going to examine the other state estimation problem of examining where planets or asteroids might be. We're solely going to focus on artificial satellites. So orbit determination, or state estimation, in order to predict where something will be, we have to know, we have to have a set of parameters that will allow us to predict its future motion. The minimal set of parameters that allow us to do that are the position and velocity vectors at some epoch, time t, right? Later we'll include the dynamic and measurement model parameters in our estimation in order to give us a better estimate. And really all we're trying to do here by taking those set of parameters is get the best estimate, or the essentially what our true value is from the observation and the reported state. So having that position and velocity and predicting those position and velocities at an epoch over time, and creating a table of those position and velocity as a function of time is actually called generating an ephemeris. So an ephemeris is a table of the position and velocity of that satellite at some time t, right? So when we generate those ephemeris, obviously they're not always correct. So why are they not always correct? Well, really they differ for two reasons. Some inaccuracy in the estimated state vector, and some error in the numerical integration. So we have position velocity, right? So velocity is simply the derivative of position, same thing for acceleration. So when we're integrating, we may get some errors from the numerical process that we use. And in our estimated state vector, maybe we have some approximations that we made in the model. Maybe we have some random or systematic errors in the observations that we made. Maybe there's some error in the computational procedures. Maybe the code that we used, doesn't take into account some effect. Maybe we're using a certain propagator that doesn't take into account the atmosphere for a low Earth orbit satellite. So moving on, so now, okay, we kind of have an idea of where our errors might arise in estimating that dynamic system. So let's take a look at the estimates themselves. So again, inaccuracies arise from estimating the state vector and from numerical integration. And as we go further on from this point, if you start to feel uncomfortable with what we're doing, you should go back and you should review Appendix A and B in the textbook. Appendix A is probability and statistics, B is matrix theory. If you haven't already been exposed to these, we're going to get into these very heavily later on. So if you feel uncomfortable with these now, then you should probably go back and review these. I do have notes on Appendix A already up on the website. At some point we'll do Appendix B, but it probably won't be anytime in the near future, so you should go back and take some notes yourself. So we're going to start to look at an example or a way to illustrate the orbit determination process. So if we were to make an estimate using a uniform gravitational field, we would see three trajectories. We would see a true trajectory, so where the satellite actually is, a nominal trajectory, which is where we want it to be based on if our model was perfect and if our observations were perfect, and the estimate trajectory, so knowing that we have errors in our model and in our observations, the estimate is our best guess, or essentially our best estimate of where the satellite actually is. So we're going to use x as our state vector, and what goes into that is our observations, the location of the observation, so your ground station, and the method that you use to estimate that state vector. So what you're looking at is what we just talked about on the previous slide. We have our observations, our row and our row dot, so our range and range right, and then we have our elevation and our elevation rate, so theta and theta dot, and that is provided from a tracking station on the ground on some mountain in this 2D case. And as you look at the screen, you can also see the estimated trajectory, so our best guess of where it actually is, the true trajectory where the satellite actually is, and the nominal trajectory of where the satellite should be. Now, you'll also notice that we include g, or the gravitational acceleration, in this case as well, because that comes from our model. So we have to observe the satellite overhead in order to predict where it will be in the future, right? Remember, we're getting that position and that velocity at some time or some epoch, right? So if we know the derivative, or we know the rate of how that state vector changes, then it's simple enough to update that state vector. So our state vector is actually inherently linear. As you can see, we just perform a operation on the on the derivative of that state vector in order to give us our new state vector. So for example, the state vector at some time t is equal to the initial state vector plus the rate of change times t. We can't observe the individual state components directly, so I can't observe the position x without observing others, and that's because our observations are nonlinear. So when we're looking at, you remember we looked at our range rate, elevation, and elevation rate. They are nonlinear, so we have to find some way to to linearize these in order to solve for the state vector components. So transforming our observations into the best estimate, we can take our observations and then the function g, which is a nonlinear vector that is simply the equations in the previous slide, giving us the observations from the state vector from our initial state vector. So as you can see, we have a range, our elevation, and then our range rate, and then our elevation rate. Well, we're just going to the matrix theory here, and we're essentially trying to build up to that Newton-Raphson iteration where we're doing that root solving, where we have our observations minus what the state vector gives us in terms of our observations in order to attempt to try and linearize this a little bit, or at least make it easier for us to solve since it's nonlinear. And because it's nonlinear, now remember that you may have multiple minima and multiple maxima, multiple solutions may exist. So not all of the observation information may be available. So what if one of your sensors is out? Or what if you have some device that only can take range? Well, in that case, because remember degrees of freedom, we need our four variables to solve for our 4 state vector variables. So we need our 4 observations to solve for those 4 state vector variables. Well, if we don't have all 4 observation variables, then we have to take them at different times. So let's say we have our range and our elevation available. Then we would have to take 2 observations. Or if we only had our range, then we'd have to take 4 range observations in order to meet our degrees of freedom or our state variables, our 4 state variables in this 2D case. So both approaches, where we have all the observation information and where we have to take multiple observations, assume that we have perfect knowledge of the governing differential equations, which, as we've alluded to earlier, the models may not always be accurate, and that we have perfect observations, which we also said observations may suffer from random and systematic errors. But in this case, we're assuming that we have perfect knowledge of those governing differential equations of perfect observations. And so this is kind of leading up to the classical case, classical orbit determination, where number of observations or number of variables from those observations directly to those state variables, where we have 4 to 4. But the modern or general orbit determination, we take multiple observations, more than necessary, and use normally a least squares criterion or some fitting method in order to try and reduce the random and systematic errors that arise from our observations. So typically, because remember our observations are nonlinear, we can actually get a best estimate by linearizing the problem. So that basically means that we're going to expand the equations of motion and use the Taylor series in order to try and get that best fit. So that's actually leading up to where we start looking at deviations from a reference trajectory. So remember we talked about our nominal trajectory, right? Well, the nominal trajectory is the model that we have, and the variance or the deviations, we want to minimize our variance in order to find the best fit with those observations that we have. Again, typically based on least squares criterion. And so that means that we're going to have this perturbed state where we have the true trajectory is actually equal to the nominal trajectory plus some perturbation, right, or some deviation. And we're trying to minimize, we're trying to find, based on that deviation from the nominal state, we can estimate what our true trajectory is. So again, that's just, as you can see, the perturbed state is just subtracting from the nominal, subtracting what we've observed from the nominal, or our true trajectory from the nominal trajectory. So in order to linearize this, you just expand, you go to those observations and you expand you take these equations and you expand them using the Taylor series about the nominal trajectory. So rewriting this, we actually end up with a linear equation where we're mapping the state vector perturbations to the observation perturbations in order to try and get some fit. Excuse me. So the state transition matrix, moving on from this point, the state transition matrix is actually going to update the deviation vector. So in other words, the state transition matrix maps deviations in the state vector from one time to another. So that means that at the initial state, the initial perturbed, the initial deviation, we can use our state transition matrix to find the deviation in the state vector at some time t. So for, and as I alluded to previously, and I mentioned on this slide again, classical orbital determination, the mapping is exact for the observations to the state variables, or the state vector variables. But for general orbit determination or modern orbit determination, our state equations are going to be non-linear, and the state transition matrix is actually the linear term in that Taylor series expansion that we just saw previously, where we step into here, linearize the system using that linear algebra, and then come out here, and that's actually our linear term of that state vector at some time, at the initial time. So where this comes into play is we can actually map the initial deviation to the deviation at some time t, right? So then we go step back in, we linearize this here. So this is just taking the equation from several slides ago and plugging back in. Now, given some arbitrary epoch tk, you can actually determine the best estimate of that state vector perturbation from the nominal by using this linearized system, right? So h, obviously h tilde is going to be an m by n vector, where m is the number of observations and n is the number of state variables. Well, in the classical case, m is going to be equal to n, and in the modern or general case, m is going to be greater than or equal to n. So later on, we're going to look at how to actually use this valuable information. But for right now, for the example problem that I'm about to give you, we're just going to use the classical orbit determination and take the variables that we have and determine them one-to-one. So practice problem is going to be uniform gravitational field in the 2D case. So here's the problem definition. So given some perturbed initial conditions, so in other words, your initial conditions are not correct, you're going to use a Newton iteration scheme to recover the exact initial conditions, or at least the conditions used to produce the observations provided. Excuse me. You're going to assume that the ground station coordinates are correct. So you're going to write a computer program that computes the range from the initial state vector. You're going to compute the observations from those given initial conditions, and then you're going to iterate using that Newton-Raphson or Newton iteration scheme and solve for the correct initial conditions. So the perturbed initial conditions are x naught is equal to 1.5, y naught is equal to 10, x dot, so our velocity in the x is 2.2, and our velocity in the y is 0.5. Our gravitational acceleration is 0.3, and our ground station coordinates are 1. For our range, what that looks like is 7, 8, 8.9, 9.8, and 10.6 at time 0, 1, 2, 3, 4. So you're going to take that initial state, you're going to solve for the first range, right? And then you're going to iterate through and find the range. And then you're going to use the Newton iteration scheme in order to solve for the exact initial conditions. Fair enough? All right. Have that to me on Monday, and I'll see you again on Friday. Thanks.